All right. Hey there, calculus students. Good to see you guys. This is your congratulations. You made it through. This is your final video of the semester. Not at school today. I'm at home and just have this one video to do. And so I'm here to bring it to you. Just want to let you guys know, thanks for a great semester. Thanks for working so hard this year. Thanks for working through the challenging times that we've had. Really can't wait to hopefully see you guys soon. So also hope for a little bit of a white Christmas. That'd be great. And yeah, just hope in the new year that we get to be back together a little bit. So last topic that we want to talk about, and so we've got just a couple days left here in the quarter of the semester, and I want to make sure that we address something that's going to benefit you as we move forward. So this is not an extra thing. This is something that it's going to be good for us to see so that we talk about right after break, you know what we're doing. And here, I want you to think about f of x and f prime of x. And you know that f of x, suppose f of x is 3x squared, you know that f prime of x is 6x. But, so this had a derivative, meaning we took the derivative of this and we got that. So I want you to think of what would we have taken the derivative of to get this. I'm going to call that big F, meaning that f of x is the derivative of f. So this is big F. What did we take the derivative of to get 3x squared? I want you to think about that for a second. Think about what you could take the derivative of to get 3x squared. You think about it, you know it's got to be something to the third power. Turns out that it's x cubed. Oh, look at this one, 2x. You take the derivative and you get 2. What is it that you took the derivative of in order to get 2x? And the answer would be x squared. The derivative of 5 is 0. What do you take the derivative of to get 5? It was 5x. So we'll try to put it all together now here to see the pattern. The derivative of x to the fifth is 5x to the fourth. But if you can think of what you took the derivative of to get x to the fifth, you know it has to be x to the sixth. You know you increase the exponent by 1. Well, what happens here? The derivative of x to the 6 is 6x to the fifth. 6x to the fifth, that's not what you have. So if we put it over 6, see if we drop that 6 in front, yeah, that works out. So you can see what you had to do is increase the exponent by 1 and then divide by that. So the derivative of x to the nth, we've all learned, is n times x to the n minus 1. So if you want to go backwards, we say that it would be x to the n plus 1 over n plus 1. This thing is called the antiderivative. And to be clear, the antiderivative is it's not something that, it's like you're afraid of derivatives. You're against derivatives. It means you took the derivative of that thing to get this thing, okay? And so sometimes it's helpful to go backwards. Let me try a few more examples with you as we do this. We're not going to look at f prime anymore. We're going to look at f of x, and we are going to determine large F. So we'll do a couple examples here. And I know you don't have any notes in front of you, and that's okay. It's a very, very short lesson. Suppose you have x to the 7th or 4x to the 6th, and you want to find the antiderivative. You increase the exponent by 1, and you divide by the new exponent. That's it. So the antiderivative of 4x to the 6th is 4x to the 7th over 7. That's all there is to it. You're like, well, come on, Mr. Gantz, we know it gets more difficult than that. Well, sure it does. We could try, like, for example, say 3x squared plus 2x minus 1. So now we just do each part. So the antiderivative of 3x squared is going to be 3x to the third over 3 plus the antiderivative of 2x will be 2x squared over 2 minus the antiderivative of 1 is x. So when you simplify this, those cancel, so you just get x cubed. These cancel, leaving you with just x squared. That's minus x. So that's your antiderivative. And as you guess, we definitely have situations where, we look at radical functions as well as rational functions. So, for example, suppose we have x to the 3/5, or suppose we have 4 roots of x over 7. So in this situation, we got to add 1. So x to the, if we add 1 to 3/5, or add 5/5 to 3/5, we get 8/5. And we have to divide by 8/5. Well, now you got a complex fraction. So we don't want to divide by 8/5. We want to multiply by 5/8. So this becomes 5x to the 8/5 over 8. And that's the antiderivative. Sometimes if you have a radical, you want to rewrite it so it's got an exponent. That's in rational form. So 4x to the 1/2 over 7. And so when you take the antiderivative, we're going to add 1 or 2 halves. We get 4x to the 3/2 over 7 over 3/2. Okay? So divide it by that 3/2. Well, instead of dividing by 3/2, let's multiply by 2/3. We'll multiply by 2 over 3. We get 8x to the 3/2 over 21. Now, here's the great thing about it. I got 8x to the 3/2 over 21. You want to check to see if it's actually the antiderivative. And that's something that, as a math teacher, you want to see all your students doing, that you can verify your answer. So 8x to the 3/2 over 21. When you take this derivative, you drop the 3/2 in front, times 8 over 21, x to the 1/2. So 3 times 8 is 24 over 42, x to the 1/2. 24 and 42, those are both divisible by what? 6. So we get 4 roots of x over 7. Yeah, so it checks out. It works exactly like it's supposed to. Now, last example, I'll let you guys go. Super short worksheet for you guys to work on and be ready for Tuesday. But the last thing I want you guys to think about is this. Suppose you had f of x was equal to e to the x squared. Notice if you go that direction, if you take the derivative, you use the chain rule, e to the u, x squared, e to the u, 2x, no big deal. You get 2x e to the x squared. That's the derivative. And so, you might think that if you do the antiderivative, maybe it'd be like e to the x squared divided by x squared. But when you take this derivative, you have to use a quotient rule. And you don't come up with that. That's doesn't work out. In fact, finding this antiderivative is, well, it actually seems just about impossible. It is almost impossible. There's a way we can work around it. It requires actually a lot of calculus, more than calculus 1. And we're not going to do that. But I want you to understand that taking derivatives it's straightforward. We learn how to take derivatives very well. You become very proficient. You had no idea how to take a derivative at the beginning of this year. Now you can take all sorts of derivatives. Antiderivatives, that's a little bit more confusing. We've learned some of the basics. There are some antiderivatives that are just super challenging. We try to work through and we struggle. But it also makes it kind of exciting. I'll never forget, I was in a calculus class and my teacher put that on the board. Immediately I threw that out. And I said, well, of course that's what it is. And I saw it wasn't. And it really opened my mind to how challenging it can be to go this direction sometimes. So there you have it, your basic introduction to antiderivatives. You got just a few problems on your worksheet. Just do those. You should be fine for Tuesday. Have a great day, folks. Thanks for a great semester.